Our next speaker is Satoshi Matsuoka, who has been the director of Riken Center for Computational Science since 2018. He's responsible for developing the supercomputer Fugaku, which has become the fastest supercomputer in several categories in 2020, 2021, and now he's also heading the efforts on the next one. But he's also doing a lot of work in AI for science and pushing the frontier in that space. So it'd be great to hear your perspectives as well.
Okay. Hello, everyone. I'm Satoshi. And I'm going to speak about something completely different from the previous speaker, which, of course, was a wonderful talk. And if I had more time, I would be speaking about a lot of the AI for science activities we're doing at Riken, RCCS. A lot of cool examples, which are actually demonstrating at the Osaka Expo right now, like uploading, dissecting the very high-resolution scan images of a brain and segmenting it, and then uploading the structure to the digital world and being able to simulate it, effectively achieving something like brain uploading. But today I don't have the time, so all these cool examples I have to skip over. I'm sorry, and maybe there will be other opportunities. I'd like to talk about convergence of, or the divergence of HPC, traditional ModSim HPC and AI, high-performance AI. Because there's been lots of fear amongst the HPC community that because there's so much emphasis on AI, these companies are spending, these hyperscalers are spending, budgets that are even beyond the biggest government projects to facilitate large AI data centers, and thus the whole weight of development is shifting towards AI. And some people feel that HPC will be compromised because of this. And this, it's not just about the compute, it's about the memory, the network, storage, algorithm programming, libraries, etc. So there's so much money and also other assets like people are converged into the AI space and not the HPC space. Will it compromise HPC as we know it? So my claim is that's not actually the case. In fact, what we believe is that advances and so much money being invested in the AI space and the various innovations being made thereof will help. In fact, will help to accelerate HPC beyond what would have been capable of. And that's exactly where we're betting our money, so to speak, in building and designing and building our next generation supercomputer after Fugaku next. So from the K computer, which is a predecessor to Fugaku, which we currently run, this is now 5 years old. The speed up for most HPC ModSim apps have been nearly 2 orders of magnitude, about 70x on the average, 70. Okay. The question we're always pondering: can we achieve similar speed up going from Fugaku in 2020 to Fugaku next in 2029, 2030? And of course, we felt it was very difficult because Moore's law is slowing us down. Moore's law is slowing down. But can we leverage all the advances that are being made to accelerate AI? Can we leverage? Can we converge? Can we help each other to achieve yet another 2 orders of magnitude or even 3 orders of magnitude speed up? And I don't have time to go over all the technical details of what we're considering, but I'll just give you a little snippet. Okay. For example, a lot of people ask, what about dense linear algebra? Because we all know that when we look at modern GPUs, then these FP64 its performance increase is deteriorating, or even deteriorate to the extent it's worse than the previous generation. For example, going from Hopper to Blackwell, the FP64 performance actually decreased. So what can we do? Well, firstly, when you think about the circuit principles, it's not really beneficial to construct a high precision matrix engine like historic arrays. It makes very little sense in the first place. That's what the vendors have been doing recently, but either they have come to their senses, or because of the pressure of AI, they're not doing it anymore. That's why Blackwell is not as fast as Hopper, despite it's a newer GPU. But it's exactly the right thing to do. Because when you think about it, laser pointer here. Well, when you think about it, did I get laser pointer? No? Okay. Well, when you think about it, you look at low precision versus high precision. And this is also a principle we know in HPC. So when you have high precision matrix multiply, like 64-bit or 53-bit multiplier, to be exact, you get very large surface area for the circuits. So you spend a lot of time and energy within that volume. Okay? But then when you compute with a historic array, you would ship the data over to the neighboring processor. But because the area is so big, you spend a lot of time compute, and then the surface area is really relatively small compared to the volume. Okay? So the energy and the time is dominated by the inners, the computation, and not in the transmission of the data. Okay? So that means even you don't really need to construct a historic array. It can very well be a vector and almost get the same results. There's not much benefit in constructing a matrix array, a matrix engine. Whereas low precision is the opposite. You get very small circuit area, and most of your energy and time is dominated by the transmission of your result to your neighboring processor, to the neighboring execution unit. So for low precision matrix multiply, it makes every sense to construct a matrix engine with historic array. And in fact, the tendency has been that we go down to from 16 bits to 8 bits to 4 bits, like in tensor core GPUs, also like things like TPUs. The matrix engine has been getting bigger because you're getting efficiency that way. Okay? So it makes very little sense to create these in the first place. And then, but what do we do when we get rid of FE64? Well, for very low precision apps like 4 bits, or even 2 bits actually these days, deep learning AI, of course we use low precision matrix multiply. For mid-tier, like 19 bits to 32 bits, we either use emulation or mixed precision. These are applications like molecular dynamics. But what about those for 64-bit dense linear algebra? There are some applications like material science codes, many material science codes handling Hamiltonians. These may require high 64 bits. So what do we do about those? Then, well, in the very old days, we used emulation when we didn't have floating point units. Then we went to hardware FE64. Now we're going back to emulation again. This is the nature of what's called an emulation scheme, and the most recent algorithm is what's called the Ozaki scheme. And we expect that we can get tremendous speed up because of this, and these were invented by Professor Ozaki. Also, there's a new Ozaki scheme too, which is about to be published, which is really Ozaki Imamura's scheme. Imamura is one of our leading team principal in my center. And I won't go into details of the algorithm, but by using the integer matrix units, they can emulate the FP64. And because these are so faster, these are 100 times faster in terms of compute as opposed to FP64 units, even if you do emulation, they're still faster. You come out positive at the end. And again, I won't go into the details, but if you read, you can read the paper. And in fact, NVIDIA is going to make it a default in the upcoming numerical library. The projection is that for Grace Hopper, you get about, the native is 60 teraflops. But if you use Ozaki Scheme 2, it'll exceed the speed of the native x64, despite the fact that it still uses matrix engine. And when you go to something like Rubin 300, and this is my estimate, 2 or 3 years down the road, the DGEM will, with the four-chip, four GPU die, multi-die package, the DGEM will have very modest increase in performance, maybe around 100 teraflops or so. But we can accept Ozaki Scheme 2 to be, with a little bit of precision adjustment for practical application, a petaflop. Okay. So, and this obviously, these performance gains were originally intended for AI to accelerate, especially the frontier models. But by using this, it can accelerate high precision HPC applications, for example, especially those in the area like material science, by order of magnitude. Okay? And we're also testing whether these are accurate. Also, companies like NVIDIA, they're also doing their own tests. There are several groups now. It's becoming a very hot research topic, whether precision requirements can be met, what are the, how can we compensate with their errors and all that. Well, what about memory-bound codes? Well, so if you do a straightforward way, the research done by one of our team members saying, if you just do a straightforward way, you really can't get much speed up because codes are memory-bound. So no matter how much you use the tensor cores, you're not going to get much speed up if you just port your applications over straightforwardly. But if you're smarter, then start using, modifying your algorithm to essentially, so this is work being done by the earthquake science team, who's also at University of Tokyo, who's also our visiting scholars, Ichimura and Fujita, that they developed an algorithm for certain cases like seismic wave propagation. Because the matrix really doesn't move, because it's wave propagation, the structural changes don't occur. So the matrix coefficients and the solvers doesn't really change much. So you only need integers, 8 bits of resolution. And so if you use that fact and modify your algorithm to compensate for the errors, then you can get speed up going from 64 bits to just 8 bits. Use tensor cores for maximum efficiency. And although these are memory-bound codes, you have some reduction from 64 bits to 8 bits. And thus, you get 8 times speed up compared to FP64. Or for some of the other, or for sparse linear solver, this is a work done by Professor Yoshida at Kyoto University. What you can do is to apply preconditioners to basically try to squeeze the range of the coefficients such that it'll fit within this range of a very small number, a very small range afforded by these low precision numbers. Again, by doing this, we can get very high speed up. Because we're using smaller numbers, there's less data transfer. So we get 4 times speed up, 8 times speed up. And we're developing tools too. So what happens? Is this real? Can you tolerate the errors? So our team is developing, led by Jens Duncan, also with Viv, they're creating tools to allow for analysis of the algorithms. When we reduce precision, will it break, or what are the errors? What errors it may occur? Will it break the application, or is it safe? And make it very easy to analyze the existing codes. And we have done it for like FlashX, for the Berkeley FlashX, to prove that we can actually reduce precision and be able to still get the same number. And this was done without any change in the code, but doing the analysis. Okay, so I'm running out of time. So, and there are more, like how do we modify code using the foundation models in the correct way? What about the interconnect? What about the other things? But finally, so combining all those. So we've been working with Furaku Next with, now this time, not just with Japanese vendors, but our usual suspects. And after 3 years of intense research on the strawman architecture, we came to the conclusion that we can get tremendous speed up in 2029, 2030. We can achieve almost zettascale performance in AI, still within the 40 megawatt bound of Fugaku. Fugaku Next. Fugaku Next facility will probably have 40 to 50 megawatts. So assuming the cap is 40 megawatts, we can achieve, in 2029, 2030, we can achieve almost zettascale performance in AI. But for normal HPC codes, we can only achieve factor 5, factor 10, maybe factor 20 in raw hardware. So if you run the same code, okay, then you only get factor 5, which is still pretty good. Then you get 5 exaflops or 10 exaflops. But it's modest speed up. But if we apply these techniques, or manual techniques that it couldn't introduce, then we believe that although the hardware gains modest, but by introducing various methods like mixed precision, or exploit the network, change the algorithm, et cetera, we can get another nearly order of magnitude speed up. Then what I couldn't get into is the use of surrogates or physics or neural network, like using surrogates to using AI to simulate the simulation. We can get additional 10x, and there are lots of work we're doing in this area as well. So all combined, we can get 200x to 1000x, because these are orthogonal. These are orthogonal things. Okay, so we can get at least another 100x as we have achieved from K to Fugaku to Fugaku Next. And of course, our AI performance will be more than 2 orders of magnitude faster compared to Fugaku. So advances in AI hardware, hardware supporting AI, will not only accelerate AI, but with smarts, with the right design, system design, with the right algorithms design, with innovative algorithm design, we can achieve much greater performance gains into the zettascale era. And that's what we're aiming for in the next 5 years. Okay, thank you very much.